Chapter 3 is on energy, work, and metabolism. As I said, we're going to do a quiz on this chapter come, let's say, March 3rd? Yeah, March 3rd. So we'll have a quiz on this come March 3rd. That's after the Mardi Gras break. We'll probably have covered much of the chapter by then. But we're going to look a lot at this sort of energy, but then later in the body section, the A&P section, we'll look at the metabolism of the body. It's a very interesting chapter. Energy is the ability to do work. And this isn't work like you think of, like, oh, I have a job and I'm going to go to work. This is the physics definition of work, and the physics definition includes both force and a displacement, or a distance. So work is done when a force causes a displacement. If an object has a force acting on it, but no displacement, then there is no work. And the opposite of that is true as well. Can you think of a situation where an object has a force, but it doesn't have any displacement? Remember, displacement is just moving from one position to another. Can you think of such a situation where you have a force but no displacement? How about you? You folks? You have forces acting on you? Are you being displaced? Are you moved around? No, you're not moving, right? But you have like a gravitational force that's pulling down upon you, but you're not traveling downward, so that gravitational force is not doing any work on you. Likewise, if I have a displacement but no force, then that's also no work. Can we think of a thing that will have a displacement but no force acting upon it? That is something that's traveling at a constant speed but no force acting upon it? Sure, like, I don't know, things just traveling through space, or a ball rolling, that there might not be any forces that are causing its forward motion, that it has inertia, and so it's continuing on in whatever state of motion it was, but there's no net force acting upon it. So if an object is moving, then it must have had work applied to it. So there's no net force acting on a constant speed object. That was the first law, the law of inertia. But there must have been something that happened in the past to get an object to move, right? Like if I have an object moving through space, there must have been something that caused it to move at some point. So work is the product of the displacement and the component of the force in the same direction. And I'm going to give the definition as just work equals F times D. But actually, there's a more specific definition. So let me give you that, and then I'll generalize it. Or, yeah, I'll generalize it. I'll make it more palatable. There's actually a cosine of theta term. And what this cosine of theta term does, don't worry, you're not going to have to do a cosine. But what it does is it takes a component of the force in the same direction as the displacement. So if I imagine this guy that's pulling a block along, he's applying a force that's up and in this direction. Remember how we talked about you can take a vector and break it into two separate components? I can break this vector into a component. Part of it is pointing up. I'm going to call that Fy. And then part of it is pointing to the right. And I'll call that Fx. And so the x component, or the force the force in the x direction is in the same direction as the displacement. So if I wanted to rewrite this equation, I could say that work is equal to F of x times x. And those would be identical equations. I'm just making it more general just for the x direction. So the force in the x direction times the x displacement will give us our work. Does this force, Fy, does it do any work? That y component of the force that he's pulling on this block, does Fy do any work? All right, let's do it as a quicker question. So Fy work? A yes or B no? Is it just rainy? Is that the problem? You seem very, well, you don't really want to be here, do you? Is that true? You don't want to be here?
It's difficult to wake up in weather like that.
Okay.
It's perfect for nap time.
All right.
Lie.
It's 9 o'clock. It's too late for nap time.
It's not true. Not true.
Okay. Does Fy do work? Does Fy do work? Okay, let's stop at 30. Hey, Deshaun. Okay, Fy does not do work because in order for a force to do work, you have to have the force and the displacement in the same direction. So that's where this comes about, that Fx times x is equal to the displacement. But if I were to write the same thing, say that the work is equal to Fy times y, and that would not be incorrect. But the y displacement here is equal to 0. So the work is also equal to 0. So in the case of this force, it's like the gravitational force acting on you, that it's not causing any displacement at all. So this force is not doing any work, and this force is doing work. No work, work. No work, work. So I have to have both a force and a displacement in the same direction in order to have work. We're going to talk about, so we're going to talk about actually if you have force in the opposite direction. But first, let me just reiterate that. So if the force is in this direction and the displacement is also in this direction, that's positive work. If the force is in this direction and the displacement is in that direction, that is work equal to 0. A third situation I might have is what if the force and the displacement are opposite? So what if my force is in that direction, but my displacement is in this direction? And in this case, this is going to be work that is negative. Okay? So if the force is in the opposite direction of the displacement, that is negative work. We'll begin to talk about this in the terms of energy. Work and energy are very, very simple. That if I do work on an object, I will give it energy. Watch this. If I do work on this object, I've applied a force in that direction, and it's moved in that direction. Have I done positive or negative work in that case? Force, displacement, same direction, that's positive work. And I've given that object energy. On the other hand, when I do this, there's another force acting on it. What's the other force it's acting on in the horizontal direction? There's a frictional force. And what is the direction of the frictional force? The object's moving this direction. It's the opposite direction. I think that was a question in your test. So the friction is in that direction. The displacement is in this direction. The frictional force is in this direction. So they're opposite. That means that the friction is doing positive or negative work. Negative. So that means that instead of the force giving energy to the object, it's taking away energy. And that's why the object slowed down, because the frictional force was doing negative work. That means that it was taking away energy from the object. So let's write that in words. So If it's doing negative work, it's taking away energy. And I'll write here also that it's like friction. Friction almost always does negative work because it always opposes the direction of motion. And if it does positive work, it is giving energy to the object. Okay? I would expect some questions about that on the test in a few weeks and on the quiz on March 3rd, the March 3rd quiz. All right. Let's try these questions. So which of these forces, which force does no work? And in each of these, the block in the figure is moving to the left. So these are 4 distinct situations. And in each of them, the block is moving from right to left. It's moving to the left. So in which one of them is there no work being done at all by the force? All right, let's stop at 55. We're just answering the first one right now. Okay, good. A is the right answer. That force is doing no work because the displacement is in this direction and the force is perpendicular to it. So that has work equal to 0. Which force does negative work? And remember, on all of these, the displacement is to the left. All of these are moving towards the left. How do you get negative work? What has to happen in order to have negative work? Right, so the force and the displacement have to be in opposite directions. The displacement in this case is to the left. And so I want to know which of these forces does negative work, A, B, C, or D. I'm sorry, what now? Yeah, I'm saying all 4 of these blocks are moving to the left. And then there's a force. There are other forces perhaps working on them, but all these objects are moving to the left, and there's a force acting upon them. I want to know what is the work done by that force. Oh, no, the little arrows? No, you don't pay attention to those. Okay, yeah, I'm sorry. I don't know if I actually said this, but these are just, these little arrows right here just designate that those are vector quantities. So it's not showing the direction of the force. I'm sorry. Okay? Okay, that's a little bit better. Good. So, all right. I'm going to stop at 148. 148. Okay, very good. So C is right. The force that does negative work is the one where the force is in this direction and the displacement is in this direction. And so that is negative work. Oh, how do you get a baby astronaut to go to sleep? You rock it. Okay, so for this one it was A, this was C. The force that does positive work, I'm not going to do this as a clicker because there are actually 2 answers, right? There are 2 answers for this because both B and D will do positive work, although D, only a component of that force does positive work. So the X component, Fx, right here, will do positive work. On the other hand, Fy does no work at all because there's no displacement in the y direction. And then the force that does the most work, it depends. Are you looking at positive or negative work? If you're looking at positive work, the force that does the most work is would be B, because it does the most positive work. So B has the most positive work. Let me explain again. I'll write this down in just a bit. But positive and negative work. Positive means I'm doing what? I'm giving something. What am I giving? Energy. I'm giving energy to the object. It's like pushing the desk. And negative work means I'm taking away energy. It's like a frictional force. Let's write that down. So negative work takes away energy. And positive work gives energy to an object. Okay, let's try some of these quicker questions. Is it possible to do work on an object that remains at rest? All right, let's stop at 30. Okay, not possible to do work on an object that remains at rest. Because if it's at rest, what is its displacement? It's 0, right? And if its displacement is 0, that means that it can have no work. So work is equal to force times displacement. If either one of those things is equal to 0, then there is no work. And so in this case, if D is equal to 0, then that means that the work is equal to 0. All right, what about a box being pulled across a rough floor at a constant speed? What can you say about the work done by friction? Okay, let's stop at 35. 35. No, they're good questions. All right. I can hear you when you say stuff like that. Listen, in my other class, I'm over in the business school. Other classes in that auditorium over in the business school. There are like 100 people in my class, and the room is sort of shaped like a bowl. Have you ever seen one of those things? They're like at science museums where they have two dishes, like they look like, I don't know, radio dishes that are opposing one another, and you can stand at one of them and whisper, and then the person in the other one can hear you. You ever seen one of those? That room is sort of like that. So I can stand here, and Aaron, about where you are, there are two young women that sit, and I can hear just their conversation. Even though I can't hear anybody else, I can just hear them. And so they'll say things, and I think they're talking to me because I can just hear them so well, because it's like standing at the little radio dish. It's like the focus of the room is at the front where they are. Anyway, what was I doing here? Friction does negative work. C is right. All right, how do we get on that? Oh, you said you didn't like the questions. Yeah, so friction does negative work. So remember, if F and D are opposite, then that's negative work. Let's look at this scenario. I'll just draw a picture right here. If I have a block and it's being pulled across a rough floor at a constant speed, let's say it's going in this direction at a constant speed. At a constant speed, by the way, means that the acceleration is equal to 0, right? That's what constant speed means, that the velocity is not changing. And so I must have two forces acting on this in order to cause this object to move at a constant speed. I have one force that's going in this direction. That's like the pull force. And then I have this force, which is in the opposite direction. That's my frictional force. I have two forces, and both of them are doing a different type of work. So the first force, which is a force acting over a displacement, is doing positive work. And the second force, which is also a force acting over a displacement, is doing negative work. How do these two forces compare? Is big F bigger than the frictional force? Is my pull force bigger than my frictional force? Or vice versa? Or are they what? How do they compare? Are they the same? F, bigger, smaller, are the same as the frictional force. Bigger, smaller, are the same. It's the same, right? And I know that because the acceleration is equal to 0. And if the acceleration is equal to 0, that means that the net force has to be equal to 0. That was Newton's second law, right? F equals ma. That if A is equal to 0, then the net force is equal to 0. So these two forces have to equal one another in magnitude. That means also that these two works are going to be equal but opposite. And so I could say that the net work done on this object is equal to the positive work minus the negative work. And so that would be equal to 0 work. So the total work that's being done on this object is 0, but we'll often talk about the work done by an individual force. Okay, that's a lot about work, I understand. But it's important as we move into energy because the two are very related.
Is that saying that the positive work and the negative work is equal?
Oh no, it's saying that I'm subtracting the two. I'm saying, like, if this is 3 joules and the other is minus 3 joules, then that's equal to 0. Okay? Kinetic energy is the energy of motion. You're not going to have to use the equation for kinetic energy, but I absolutely want you to know it. It's on the equation sheet, and I'll ask you some questions about it, but I won't ask you to calculate the kinetic energy. But the kinetic energy is equal to 1/2 mv squared. Sometimes we use K. Sometimes I might slip into using KE. In my other class, I use KE because we use K for something else. Here, m is the mass, and v is the speed. Okay? What I want you to recognize here is that the energy is proportional to the mass. So if I doubled the mass, I'd double the kinetic energy, for example. But the kinetic energy is proportional to the square of the velocity. So if I doubled the velocity, I would quadruple the kinetic energy, for example. If I doubled that quantity, I would quadruple that one. Whereas if I doubled the mass, I would only double the kinetic energy. So the kinetic energy is more dependent upon the speed than it is on the mass because of that squared term. That's really all you need to know, and you'll see some questions. I might ask you some here about those. Okay? Can I go down? This is all in your book, too, so read that chapter as you prepare for the quiz. You know, the quizzes can include things that aren't in the class, so you need to be reading those chapters anyway. Usually it doesn't, but it can, so you need to read the chapter. If you do work on an object, the energy changes. We talked about this. The work is equal, then, to a change in energy. This is called a work energy theorem, or the work energy theorem. And usually we'll use it to describe a particular type of energy, which is the kinetic energy. So we'll say that work is equal to a change in the kinetic energy of the object. Okay? Do these two questions. I'm going to go ahead and start the thing. I need to go to my office and grab something I forgot to bring. And then when I bring it back, I'm going to show you something. So do these two questions. Just click in on the first one, and then as soon as I come back, I'll open up the second one. Okay, I'm going to stop at 138, and then I'll open up the second one. Okay, good. A is right. If I push a car to, oh wait. Okay, I'll give you, I don't know. I'm not going to mark anything right. Because really the answer that I intended was B, that the total work, but A is not entirely wrong. I think maybe you just didn't understand the question. Really what I was asking is what is the total work done? And if I'm looking at the total amount of work, then it's sort of like pushing the block with the frictional force acting, that I have one force that's doing work in this direction, and then I have another force that's doing work in that direction. And so the total amount of work that's being done by both forces, they're going to add up to equal to 0. So for example, this force might do 10 joules of work, this force would do minus 10 joules of work, and that means that the total amount is going to be 0. Okay? So I'll just give credit to all of you. It's definitely not negative. Well, the frictional force is doing negative work, so I just need to be more clear on that question. All right, you'll click in with this last one. What are the units? What is the unit of work? I didn't give this to you, but I think that you can figure it out just by looking at the formula for the work equation. Do you remember what the work equation was? That work is equal to the force times the displacement. So if you put in the units for those variables, then that'll give you the units for work. Okay, I'm going to stop at 53. 53. Okay, good. A is right. Anytime I ask you for the units of something, always go back to the equation. Find the equation on your equation sheet for that particular value, and then just put in the units. Because I know the units for force are newtons, and the units for displacement is meters, and so that's why I know it's Newton meters. Another question that I sometimes ask is what are the basic SI units? And so if I were to find the basic SI units of work, then I would say, well, I know it's something times meters, and the value for newtons, or the units for newtons, is mass times acceleration. So it would be, I would say, mass times acceleration times displacement. That would be kilograms, meters per second squared, times meters. And so the basic SI units would be kilogram meters squared per second squared. Okay? Even though we've moved on from chapter 1 and all the other chapters, like the tests aren't cumulative, they sort of are cumulative. You'll see that. It won't be a surprise. But you'll see some of these topics that'll come back, like dimensional analysis, might come back in a later test. But it won't be a surprise. You'll know when it's coming. The units of work and energy are the same. Work is given in units of Newton meters, and energy is in joules. The unit of energy is a joule, and 1 joule is lowercase when it's written out, but when it's abbreviated, it's uppercase. Do you know, by the way, how you determine? It's a good grammar lesson for you. When some units are capitalized and some are not, do you know why? Right, yeah, it's after somebody's name. Like a Newton is after Isaac Newton, or a Watt is after Mr. Watt. And this is after James Joule, I think was his name. He was a physicist back in the 1700s, and he did a lot of work with energy. So a joule is equal to 1 Newton meter. Okay. Yeah, we'll do that later. Potential energy is stored energy or work. We'll talk about this in the context of the body, because the body stores potential energy. This is stored energy or work. There are lots of different types. There is a elastic potential energy. And an elastic potential energy, oh, I don't have a rubber band. But if you have something that's stretchy, if you stretch it out and then you let it go, it's going to shoot off and become, go off into another direction. So if I have, say, a rubber band and I shoot it at a person, I'm converting elastic potential energy into kinetic energy. So it's the potential to the potential to have motion, stored up energy. There's other type, gravitational. Does this object have stored energy? It does, and I can release that stored energy very simply. I can just throw it off my fingers. And then that stored gravitational potential energy becomes kinetic energy. We have chemical. Talk about that later in the form of food. Nuclear. We have a whole chapter on nuclear physics at the very end of the semester, so we'll just talk about it then. And then electric energy. We have a whole chapter on that. So these different ideas will come back periodically. All right, so let's say that I move an object of mass m to a height h. That is that I have this object, m, and I move it over a distance, h. What work have I done in that motion? Moving an object m to a distance to a height h. So I have to exert some force on this object to move it up through that distance. What work does that force do? And I'll remind you that work is equal to the force times the distance or the displacement. All right, about 13 of you have it right now. Ask around your neighbor is about that same amount don't have it right. Ask your neighbor what they put, okay? See why they did it. Okay, the key here is I need to know what F is. We've seen this before in a previous chapter, and if I do that, I can figure out what the work is. I'm going to stop at 125. 125. Okay, good. C is right. The work that's done is equal to the force times the displacement. The force that I have to exert to overcome the gravity is m times g, and then the distance is h. So the work done to move this object, I have an object of mass m. The work done to move it through a height h is equal to the weight of the object times the height that you move it through, mgh. That's on your equation sheet, that formula, that U is equal to mgh. Oh, well, here you go. I'm going to write down here. So U is equal to mgh, and that is on your equation sheet. Sometimes, I'll try to be careful, but in my other class, we call this potential energy like PE, but your book uses U, which is really the more standard variable to use. So I'll try to stick to that. But if I slip and call it PE, that means potential energy. Not like we get to go out for recess, because we don't do that like we're adults, and that's for kids. Now, recess is for adults too, right? But not right now. Okay, let's, here H refers, is that really important? No, don't really worry about this. It's not that important. Your book talks about it, the whole reference point thing, but it's not going to come up. When you drop an object, the potential energy is converted to kinetic energy. So just like I did before, the pen, it has the potential for motion. If I drop it, that potential then becomes kinetic energy. If I have an object up here, U, it has U. If I drop it, all that U now has become kinetic energy. So I've moved from having just potential to having just kinetic energy. Let's try some of these. By what factor does the kinetic energy of a car change when its speed is tripled? So if I triple the speed of my car, how much does my kinetic energy change? Look back and find the formula for kinetic energy. K was equal to 1/2 something. And then tell me if I triple that speed, what's going to happen to my kinetic energy? All right, let's stop at, I don't know, a minute. It's a dreary day, huh? Does your brain not work the same on rainy days? No? Well, we didn't have our test today. All right, let's stop at 108. Okay, C is right here. You'll probably have some question like this. Look, and the way that you do it is you say, well, I know my kinetic energy is 1/2 mv squared. You see, that's on your equation sheet, but you need to know how to find it. And then I'm asking, what happens to the kinetic energy when my speed is tripled? And so if I triple my speed, because that speed is squared, I have to do the same thing to the left-hand side of the equation. So I have 3 squared on the right-hand side, so that means I'm going to have a factor of 9 on the left-hand side. Okay? I like questions like that. They're kind of important. They'll come up probably on your various standardized tests. Not calculation problems, but just mathematical relationships. I'm done. Go ahead.
So like the half doesn't mean anything?
No, the half doesn't mean anything. Only thing that I'm worried about is the two variables. So I'm worried about what happens when the speed is tripled to the kinetic energy. Okay? The half doesn't matter. The m doesn't matter. I'm just looking at those two variables. Okay, let's try this. The second question. I have a car, and I get on the highway, and I first go from 0 to 30 miles an hour. And then I go from 30 to 60 miles an hour. I want to know which one of those requires more energy. The first part, the second part, or are they both the same amount of energy, going from 0 to 30 and 30 to 60? Okay, you're sort of split between A and B right now. Let me help you, I think. I'm going to draw the function for kinetic energy versus speed. Do you remember this from high school? I don't know, advanced math, maybe math? This is a quadratic function, and it looks like this. If I draw the function for kinetic energy versus speed, it looks like this. It's a parabola. Okay? That's a parabola. And so what I want to know is, how much energy does it take to go from 0 to 30 versus 30 to 60? Let me show you all over here. So I'm asking, which takes more energy, to go from 0 to 30 or 30 to 60? Which takes more energy to increase those speeds? Okay, I'm going to stop at 140. 140. Okay, we're still sort of split, but the answer is B. So let's put some numbers on it. Hopefully you'll see a little better. So let's say this is my 30, this is my 60 mile an hour mark, right? It has numbers on the axis. At 30 miles an hour, I've come to an energy at this point. So let's put a number here. I'll say this is like 10 joules, and so that would make this about 50 joules. Just sort of looking at my scale, that's about another 4 increments up. And then to go from 30 to 60 means that my energy has to increase by that amount. So going to 0 to 30 on this scale takes 10 joules of energy. But then going from 30 to 60, because I have this quadratic relationship, because the kinetic energy is so heavily dependent upon the speed, kinetic energy is proportional to speed squared, this is going to take a lot more energy. It's going to take like 40 joules of energy. Okay? In fact, those are the right numbers. I just made them up, but they are the right numbers. Because here I'm going from 30 to 60. I'm doubling my speed. So how much more energy is it going to take? If I double my speed, by how much should my energy increase? By a factor of 2? I double my speed. Should it increase the energy by 2? By 4. Because it's a quadratic relationship. If I double my speed, it quadruples the kinetic energy. That's why cars, if you drive really fast, and y'all drive fast? I don't. I try, yeah, I see you drive fast. I don't like to drive at all. I usually just forget my wallet. That's my trick. If you forget your wallet, then you can't drive.
But it's on your phone.
No, I don't have it on my phone. But I don't have data on my phone. I don't even really have cell service. I just have like this phone that I carry around. My wife gets all of my text messages and stuff. I told her she's not my secretary, but I have it set up so that all my text messages go to her phone because I don't ever answer text messages either. And so that way, if I get an important text message, she'll say, "Chad, you have a text message that you should address." It's a really sweet deal. And then the same way with driving. Then if I just forget my wallet, then she'll drive. Okay. Do not tell her I said that. Because I love her very much. Yeah, right. Right. Okay. So mechanical energy. Your book talks about this, and I guess it's useful. And you'll see some questions about it. The mechanical energy is just the sum of the potential and the kinetic energy. Let me just write. The potential, we're talking about gravitational potential and our kinetic energy. So E then would be equal to U plus K. That's just our total mechanical energy. And it includes energy from position. Potential energy is an energy of position. An object here has so much potential energy. If I change its position, it can have more or less potential energy. So that's what I mean when I say that potential energy is an energy of position. It depends upon where the object is. And motion. And motion is kinetic energy. There's a law called the conservation of mechanical energy. In other books, you might just hear it called the conservation of energy. But in this, energy transforms from U to K, or vice versa, or from K to U. But the total amount of energy remains the same. Bless you. You'll have a question like this. So an object that's moving up and down. A roller coaster is a good example, but I use other examples in old text. So I have a little roller coaster car, and it goes down, it goes up, it goes down again, and at each point, its potential and kinetic energy will change. So up at the top, I'm going to have a big potential energy, and if it's at rest, I'll have a kinetic energy that's 0, so I'll have no kinetic energy. That's if V is equal to 0. Okay? Where is the kinetic energy the greatest? At A, B, C, or D? Where is the kinetic energy the greatest out of those points? A, B, C, or D? Okay, there it goes. Go ahead and click in. Where is the kinetic energy greatest? I told you that the potential energy is greatest at point A. I just said that. That it has a big U and no K at point A. But where is the kinetic energy the greatest? Remember, the total amount of energy is always the same. It's conserved. It will always be the same. So where is the kinetic energy the greatest? Where does it have the greatest energy of motion? All right, let's stop at 48. 48. Okay, good. B is right. The kinetic energy is the greatest where it's going the fastest. And so down here is where it's going fastest. And actually down here, this is a height equal to 0. So U is equal to 0, and K is at its maximum. Where are U and K equal to one another? A, B, C, or D? Where does it have equal amounts of potential and kinetic energy? Okay. Absolutely expect a question like this on the test. You'll see them on the old test. So most of you have it right. I'm going to stop at 40. Ask your neighbor if you're not sure. A few of you don't have it. Remember with the clicker questions, by the way, that if you get them right, you get double credit. So if you're falling behind on clicker questions, just sit next to somebody that you think always gets them right and just ask them what the answer is. Okay? And you'll catch up in no time. All right, so C is the right answer here. I know that because the height right here is half the maximum height. And so it's like at that halfway point where it has half of the total energy is in potential energy, and half of the total energy is in kinetic energy. So at this point, at C, U is equal to K. All right? So let's put some numbers in it. Let's say that the total energy is equal to 4 joules, for example. Then here, U would equal to 4, and K would equal to 0. Down here, U would equal to be 0, and K would be equal to 4. And over here, U would equal to 2, and K would equal to 2 joules. So you see, you always have the same amount of energy, the total amount of energy. They just swap it back and forth. All right, so just your book has paragraphs about each of these different types of energy. Let's sort of go over them briefly because we're going to talk about them. We have whole chapters on most of these. Electrical energy is the energy of charges. Energy is greatest when charges are closer. Because the forces are greater. So we'll have a whole chapter on this coming up soon. If I have 2 positive charges, are they going to attract or repel one another? They repel one another. Don't worry, we'll jog your memory. I know y'all seen that in science. Middle school, elementary school science. That if I have 2 positive charges, they're going to repel one another. We'll have a whole chapter on this, don't worry. If I bring those charges together, closer, what happens to the forces acting upon them? Do they get bigger or smaller? Bigger. It's kind of like magnets, right? If you have magnets that are far away, you might feel a weak force, but if you bring them really close together, the force gets bigger and bigger. So here, the forces are going to be a lot bigger. And so the energy of charges is greatest when the charges are closer because they have a bigger force. The forces are greater. And so you can imagine that if I have two charges that are far apart and I let them go, they're just going to sort of meander away. But if I have them really close together, they have really big forces acting on them, so they have a lot of potential for motion. If I let them go, they're going to fly away really fast. They just have greater potential for motion. Internal energy, we talked about this actually last chapter, is the potential and kinetic energy of molecules and atoms. So if I have gas in a container, the atoms or molecules will move around in that container, the interaction of molecules causing a pressure in that container, and it gives a certain amount of energy. Remember, this was the ideal gas law that we used to describe this, PV equals nRT. And so if I give it a higher temperature, then that means it has more energy. Those things are just moving around more, and it also means that they'll have a greater pressure. Heat is the transfer of energy from a hot to a cold object. When heat is added, the temperature increases or changes phase. We'll talk about phase change. You might know what I'm talking about, but if you don't, that's okay. We'll talk about that. Well, we're sort of closely related to this is thermal energy, which is an energy that's measured by changes in temperature. I brought a couple of things here. Let me show you. They're just some ball bearings. They're about a pound each or so. And if I crash them together, what's going to happen? They make a sound. Let's do it. All right. Y'all hear that? But what's happened? I'm giving these objects kinetic energy. They have a pretty big mass. I said a pound or two each. And I'm crashing them together, so I have velocity. So what's happening to the energy? Where is the energy going from these objects? Because the kinetic energy of those stops, where's that energy going? Any idea? You think it's turning into heat, maybe? There's sound too, right? Like you can hear the sound. That takes a certain amount of energy. The sound actually doesn't require that much energy. It's pretty easy for us to make sound. I want to show you something. Oh, wait, hold it. Oh, yeah. Hold it like this. Come on, hold your stand up. I'll hit you. Right. So I want to crash the two balls onto the paper, and let's just see what has happened. Ready? Oh, what do you see? It's a hole, right? Can you smell it? What does it smell like? Yeah, let's try it again. Can you smell the smoke? Yeah. You want to try it? Hardly wonderful. It's kind of cool, isn't it? Because it's like the kinetic energy of the balls is converting into thermal energy, and it burns a little hole into the paper. You see that? It didn't tear a hole in the paper. You don't smell it? No. What's up, John? You want to try it? You want to do the balls? Okay. They all a lot of them. There's not a lot of them. They won't. Oh, there you go. Look at that. Isn't that cool? Anybody else want to do it? No? Okay. I can do it after class if you want. All right. Chemical energy is the stored energy in molecules and atoms because of their position in the charged particles. That sort of goes back to if I have two charged particles close to one another, then there are forces acting on them, so they have potential energy. And that's true in chemical reactions, that you're releasing or gaining energy based on the positions of those atoms or molecules. Electromagnetic radiation is light. X-rays, gamma rays, visible light. I have a whole chapter on that. We'll talk about the eye, which is probably my favorite organ. The acoustic energy, we have a chapter on that. And nuclear energy, we also have a chapter on that. Okay? I'm going to hand back your exams. I'll let you out a few minutes early. Because y'all are kind of useless today. No, you're not useless, but you're not really getting much right.